All right, so let's just do a review of the topic so far in Unit 3, which is intermolecular forces and properties. So intermolecular forces is pretty straightforward, right? Meaning the forces between molecules. When we look at these different forces, do you remember the basic forces, what they are? Huh? I can't hear you, Ben. Yeah, what are the different intermolecular forces? Yep. So, yeah, so ion dipole, dipole, hydrogen, and London dispersion, right? And then dipole-induced dipole, which are like when you have an ionic compound, right? That or not an ionic, a polar compound that induces a momentary dipole, right? So these different forces, okay? Let's see here. All right, so when we look at the intermolecular forces, let's look at a practice problem for intermolecular forces. Let's look at this one right here. Okay, so here's a problem. At 298 Kelvin in 1 atmosphere, let's see if I can zoom in on this. There we go. 298 Kelvin, 1 atmosphere, bromine, molecular bromine, is a liquid with a high vapor pressure, and Cl2 is a gas. Those observations provide evidence that under the given conditions, the blank. All right, so let's look at the information that we're given. So Br2, Cl2. What do we know about Br2 and Cl2? What does it tell us about it? There's a liquid with a high vapor pressure, and Cl2 is a gas, right? So forces among Br2 molecules are stronger than those among Cl2 molecules, right? Forces among Cl2 molecules are stronger than the Cl-Cl bond. Br-Br bond is stronger than the Cl-Cl bond, or Cl-Cl bond is stronger than the Br-Br bond. C? Why is it C?
Okay, so it can't be B and it can't be D because that's the
Can't be B and it can't be D because they are. Okay.
And forces among Br2 molecules are stronger. So that means I guess that is a true statement, but C is a true statement. Since Br-Br is a liquid right now, that means guys bonding together. That's a liquid, molecular forces between Br are holding.
Right. So the reasoning is for C, this is your hypothesis, and that C is the correct answer, that the Br-Br forces is stronger than the Cl-Cl cloud. Or sorry, Br-Br bond is stronger than the Cl-Cl bond. Okay, because Br is in a liquid state. Okay, Jane, do you have a hypothesis on this? As to whether what the correct answer is here? You were thinking the same thing, that Br bond is stronger than the Cl bond? Okay. But you're not certain. All right, so what do we know about intermolecular bonds? The observations provide evidence that under given conditions, like those observations provide evidence. So I'm going to say that I am almost 100% sure that the correct answer is A. All right, and we'll look at the answer together here. I didn't write this problem, so I mean there is a chance that I could be wrong, but I am quite certain that the answer is A. Why? Why? What do you think? Why is A a true statement? Is A a true statement? It is true. Is BRB is option C a true statement? We don't know, and I'm going to tell you why. What is the difference between a liquid and a gas? What is the difference between a liquid and a gas? So this here, the C is telling us the bond between the two atoms, right? So the bond, when it says bond, it's meaning the covalent bond between the two atoms, right? So the bond between Br and Br and the bond between Cl and Cl, right? The information that it is giving us is discussing the fact that Br2 is a liquid, meaning that there are more interactions between the molecules of bromine than there are between the interactions of the molecules of chlorine. Does that make sense? So the correct answer here is A. Okay. So let's look at another example. All right. Let's look at another example. How about enthalpy compound W Y. Let's see here. Boy, let's look at this one. Okay, let's look at this one. So, compound with highest BP based on Lewis structure. So here's the compound name, named butanol pentane propanoic. I do not know what that is. Propanoic acid. All right. So what is it going to ask us here? Based on the information in the table above, which of the compounds has the highest boiling point and why? Which one of these has the highest boiling point and why? Thoughts? So we've got 4 possible answers here. Butanol, because it can form intermolecular hydrogen bonds. Pentane, because it has the longest carbon chain. Pentane, because it has the most CH bonds. propanoic acid because it can form intermolecular hydrogen bonds. So let's look at our Lewis structure here. So what it's looking for is the highest boiling point. Highest boiling point. But interesting, they all have very similar molar mass. 72.1, 72.15, 74. Pretty interesting. What do you think, y'all? Which one of these would have the highest boiling point and why? So what is it asking here? So it's butanol because it can form intermolecular hydrogen bonds, pentane because it's the longest carbon chain, pentane. So which one of these answers can we just get rid of immediately? You'd say pentane? Why?
It's just saying that's a long chain. What does that mean?
Right. Why would a carbon chain, the length of the carbon chain, or the number of CH bonds have anything to do with the boiling point? It shouldn't, right? Boiling point is mostly about intermolecular forces. Okay. So I think that butanol, because it can form intermolecular hydrogen bonds, and propanoic acid, because it can form intermolecular hydrogen bonds, are the most reasonable. So the question is, which one of these two molecules can form intermolecular hydrogen bonds? What do you think? Okay, propanoic acid. Why can propanoic acid make hydrogen bonds? Because that O got the H, y'all. Yes. Remember that when carbon and hydrogen are bonded together, that does not produce any hydrogen bonding capabilities. But when oxygen is bonded to hydrogen, it does make a possibility for hydrogen bonding. Okay, same with nitrogen, right? Nitrogen and hydrogen. So D, propanoic acid, because it can form intermolecular hydrogen bonds. Let's see what the correct answer is. Yep, D, we nailed it. Good, okay. Questions on intermolecular forces so far? So remember the difference between intermolecular force and intramolecular force, right? Okay. All right. Now, let's look at a question that is related to, let's see here. Let's pick a new topic here. 3.2, 3.1. Get rid of the 3.1. Let's just look at 3.2. Okay? So properties of solids. See what it comes up with here. 3.2. We haven't gotten to 3.7 yet, so I don't want to do that one yet. Let's look at this. This seems to be more 3.1, but that's okay. All right. So we've got another table here with Lewis structures. The table above shows structural formulas and molar masses of 3 different compounds. Which of the following is a list of compounds in order of increasing boiling point? So again, we've got another intermolecular force problem here. Just looking for something about properties of solids, but it's okay, let's look at it. So let's arrange them in order of increasing boiling point. Okay, so once again, we see that the oxygen-hydrogen situation, right? So one propanol is going to do hydrogen bonding. Is acetone going to do hydrogen bonding? No, because the hydrogens are all bonded to carbons. Is butane going to be doing any hydrogen bonding? Okay, so I think that we can pretty safely say that propanol, one propanol, is going to be what? Top dog, yeah, have the highest boiling point. Okay. All right, so now we need to look at what else could be going on here. So what other intermolecular forces are we aware of? The double bond here, acetone. Okay. That's pretty bad. Okay. So one propanol is going to be the highest. So B or C, or B or D is the correct answer for sure, right? So now we need to determine, is butane or acetone going to have a higher boiling point? So what does the double bond have to do with anything, Ben?
It should be harder to break a double bond.
Sure. It should be harder to break a double bond, but remember, we're not trying to break these bonds. We're breaking the interactions between molecules of this type, right? So it's not, we're not looking at breaking this into a bunch of H's and a bunch of C's and one O. We're looking at breaking this away from other molecules of this same kind, right? So what else can we, I think it's really interesting as well that the molar mass is identical between these two. Is acetone a what? Is it more polar? So, okay, so now we need to be looking at that. Is acetone more polar than butane? What do we think?
I mean, the bottom ones may be less polar. So I'm going to say acetone is going to be a bit more polar. Let's say acetone is going to be better than butane.
So you're going to say that acetone has a higher boiling point than butane because this is more polar? What do you think, Jane? Yes, that makes sense. Okay. So which one of these options agrees with your hypothesis there, Ben? B? B as in Bravo? Yes, it would be, because butane has the lowest boiling point, and then acetone, then one propanol is the highest boiling point. B is the correct answer. Okay, B is the correct answer. And it has to do with the shape of the molecule, really. Because butane is completely symmetrical, there's very little, like, in terms of intermolecular interactions because of any kind of induced dipole or anything like that, because all of them are exactly the same shape. Whereas with acetone, acetone is mostly symmetrical, but you have this oxygen going off to the side here that creates just a slight charge, just a touch, right? And so the interactions are going to be just slightly stronger. And when you think about this in terms of like how you've seen, have you ever dealt with acetone at all? Have you ever used it to like clean stuff off? It's got a really pungent smell. It's got a really, really pungent smell. And it comes in these cans, and then you put it on your hand and it evaporates really quickly if you put it on your hand, but it stays a liquid relatively well in the can, even if the can is open. But butane is like a natural gas, right? You'd have to cool it down quite a bit in order to make it into a liquid. So that makes sense with our real world observations that we may have had in our lives as well. And propanol is like a liquid, it's a fuel that you can get. It's kind of like gasoline. Okay. Good, nice work. So let's try and find a 3.2. That says that is 3.2, but it's not really. Atomic structure, bonding, radius. This looks good. Bond energy. I think that going through these kinds of practice problems can be really helpful for us, especially going to the exam, because these are questions. Oh wait, this is free response. Screw that. I don't want to. We could do some free response. Yeah, I don't want to do a free response right now though. Let's look at this, and then we'll go to a free response. Okay. So a sample of a hard, solid binary compound at room temperature did not conduct electricity as a pure solid, but became highly conductive when dissolved in water. Which of the following types of interactions is most likely found between the particles in this substance? So this is a really good example of a 3.2 type question. So what do we think? You thinking covalent? Okay. What do you think? Okay. Ionic bonds, metallic bonds, covalent bonds, hydrogen bonds. So it's not conductive. It's a hard binary compound. What does a binary compound mean? What is binary? Two things, right? It's made of two things, okay? So a hard binary compound, this could be an alloy of a metal. This could be like a salt, right? Okay, so we know that it's binary, and we know that at room temperature, it does not conduct electricity. So based on that criteria alone, what can we eliminate from these possible options? Metallic, right? Because metallic definitely conducts electricity at room temperature, right? Because it's got free electrons everywhere and they can go wherever. Okay, so option B is off the table. What about, so as a pure solid, but becomes highly conductive when dissolved in water. Okay, so what does that tell us? Highly conductive when dissolved in water. Thoughts? So, what do we know about covalent solids? We don't remember too much about covalent solids. Or hydrogen bonds. So let's look at this. Which of the following types of interactions is most likely found between the particles in the substance? Do hydrogen bonds have anything to do with conductivity that we can think of? No, they don't. Okay. Hydrogen bonds have nothing to do with conductivity. Covalent bonds, I mean, could have something to do with conductivity, but generally not. When I read this question, the thing that really jumps out to me is that when it's dissolved in water, it becomes conductive. And that tells me it's an ionic solid. When an ionic solid is dissolved in water and it's free to move, it conducts electricity. But when it is not in water or when it is solid, it cannot conduct electricity. Okay? Ionic solids don't conduct electricity. Ionic solutions do, right? So when people say about like, oh, you shouldn't be in water during a lightning storm, the water actually doesn't conduct electricity. The water itself, the water molecules. It's the salts in the water that are highly conductive. Okay. So that's one of these that you're just going to have to kind of know off the top of your head, that an ionic solid doesn't conduct electricity, but ionic solutions do. Okay. Covalent bonds have less to do with conductivity. There's not like a hard and fast rule with covalent bonds. Some covalent bonds will conduct electricity in different states of matter or in solutions or things like that, but there's not like a hard and fast rule. Most likely found between, yeah, okay? Questions on that? So ionic bonds is the answer there. Let's look at, do we want to do a free response question on this, on the solid properties? Not really? Okay. Let's do a free response question, at least one though for today. So would you prefer to do a free response for solids, liquids, and gases, or the ideal gas law, or kinetic molecular theory? 3.3? Okay. So let's check it out. Let's do one multiple choice and then one free response. Let's look at this one. Explanation for most gases are compressible. Okay. Of the following, the best explanation for the fact that most gases are compressed is that the molecules in a gas are blank, essentially. Constant motion, relatively far apart, relatively small masses, have a real non-zero volume, or E, have move slower as temperature decreases. So just like always, which questions can we just completely eliminate? Which answers can we completely eliminate? What do you think, Jane? So why would compression be? Okay, so Ben is saying that we should get rid of A and you said E. So R in constant motion. That's kind of a general statement. I would say that most molecules are in constant motion, right? Anything that is at a temperature that is not absolute zero is moving, right? So I don't feel that one is super related. And then E, moves slower as temperature decreases. Yeah, but I don't see how that's related to compressibility. So that leaves us with B, C, and D. C, have relatively small masses. That's not necessarily true. Some gases have quite high masses, right? Some of the noble gases, like if you get some xenon has a high mass. It has a much higher mass than like magnesium, right? So the mass doesn't really matter. So we're down to B and D have a real non-zero volume and are relatively far apart.
Okay, volumes first. It's volume.
So gases have a real non-zero volume. Do we think that that statement is true? Statement of a gas having a real non-zero volume? So I would say that gases occupy a real non-zero volume. I mean, the atoms and molecules themselves do have volume. It's just unreasonably small, right? But the way that they interact with one another is more important on the compressibility. The correct answer is B, okay? Because they're relatively far apart. You can't really compress liquids, and you definitely cannot compress solids because they are really, the molecules are interacting with each other at such close range that they cannot move, like in a solid, they can't move past each other at all, right? And in a liquid, they can't really move past each other. Liquids are not, I mean, for all intents and purposes, liquids are not compressible. You can compress a liquid just a touch, just a little itty bitty amount. But the fact that the molecules are flying past each other and can move, there's space in between them that they can occupy as they pass by one another. That's the reason why gases are compressible. So I think that we would have arrived at that conclusion even without my help, right? Okay, let's look at a free response question. Comparison of CH4 and CCl4. For parts of the free response question that require calculations, clearly show the method, blah, 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 blah. You must show your work and receive credit for your answer, blah, blah, blah. Okay, answer the following questions about CH4 and CCl4. The Lewis electron dot diagrams for molecules of the compounds are shown above. Which compound has the highest boiling point? Justify your answer. The types of intermolecular forces in both substances should be included in your answer. All right, so, whoa. Oh. This is a multi-part one. The types of, so part A of this question is, what is the boiling point difference? Which one of these compounds is a higher boiling point? Okay. Thoughts? So are either of these molecules polar? So CH4, would CH4 be polar or non-polar? What do you think? Non-polar, maybe? Why? What do we need in order for something to be polar? For something to be polar, you need to have a free electron pair, right? You need to have a non-bonded electron pair somewhere. Do we have any non-bonded electron pairs in either of these? No. Okay. And they're symmetrical, right? They essentially have the same like structure. So the polarity is not something that we need to worry so much about. What else can we be looking at here? Come on, guys, you can do this. What do we think? I believe in you. So they're not dipoles. So we're not going to get any dipole-dipole in either of them. Is there a possibility of a hydrogen bonding situation? No, because you've got hydrogens here, but they're bonded to carbon, so that doesn't make anything happen hydrogen bonding wise. What about chlorine? Obviously, there's no hydrogen bonding there because there's literally no hydrogens, right? So that eliminates dipole-dipole and hydrogen, right? What about induced dipole? What is that? What is that all about? All right, so let's look at this. So when we look at this and we say this molecule and this molecule, they have similar structures. Which one of these is going to have a higher boiling point? We need to establish, would electronegativity have anything to do with this? You wouldn't focus as much on electronegativity? Okay. Okay. What do you think? What do you think, Jane?
Wait, so how do you tell them it's not a dipole?
Because there's no free pairs. There's no.
What's
An induced dipole is when the electrons kind of like, so it has to do with just dispersion forces, right? Dispersion forces. So what about the mass? What about the mass of the molecules? Mass of the molecule might play into it, right? Yeah. Okay. So I would say that in this question, the boiling point of CCl4 is higher than that of CH4. And the intermolecular force between them is because of the induced dipole. Okay. Induced dipole is not permanent, right? It's just a dispersion force. But it has to do with the let's see, these molecules are more masses. So dispersion force is a result of fluctuations in electron distribution within molecules or atoms. Since all atoms and molecules have electrons, they exhibit dispersion forces. The electrons in any atom or molecule may, in any one instant, be unevenly distributed. Imagine a frame by frame, blah, blah, blah. Symmetrically arranged around the nucleus. Dispersion force. The magnitude of dispersion force depends on how easily the electrons in the atom or molecule can move or polarize in response to an instantaneous dipole, which in turn depends on the size or volume of the electron cloud. Okay? So the dispersion force of CCl4 exhibits more attraction between the molecules because chlorine has more electrons. And its electron cloud is larger. So both molecules are exhibiting dispersion force attraction. But methane has much, much less of it because hydrogen only has one electron. Okay? All right. So we would say CCl4 has a higher boiling point because chlorine has more electrons, therefore a larger electron cloud, therefore interacts more strongly with other CCl4 molecules. Okay? 400 kelvins, both compounds are gases. At this temperature, which compound, CH4 or CCl4, behaves more like an ideal gas? Justify your answer, including reasoning about both molecules. What do we think? So what do we know about ideal gases? Anything? I'm actually going to stop the recording here because it's getting a little bit long.